Okay, folks, let's get this show on the road. This is all about the Pacific Decadal Oscillation. My name is Steve Hare. I'm the current chapter president of the Oregon AMS. And Dr. Nate Mantua will be up here shortly. We're working with this wired mic tonight, which I'm not used to, so maybe we'll just do it like this. There we go. Okay, we got dual computers going here, so I'm going to just move over to mine. The world of Macintosh has invaded OMSI tonight, so. Okay, current 2012-2013 Oregon AMS Executive Council. There we are. Vice President Bobby Corser, right there in the back, counting heads. Our secretary this year is Brian McMillan. Brian is not here, I don't believe. Yeah, I think he's working tonight. He's KPTV meteorologist and reporter. Let's see, treasurer and the webmaster back there, Mr. John Rainier. He will gladly take your money to renew your dues for this year, or to sign up for those who may be new. Oh, I'm racing right through. And counselors, Mark Nelson, he's working tonight, so he's not here. Tyree Wild, National Weather Service, he's right there. Good to have you, Tyree. And notice it says Crystal Stout. It does not say Tira Bishop. And I'm going to do this real quick here. We're all wrapped up there. The reason why is because Tira is, and correct me in the audience here if I misstate that, but she is part of the Oregon Air National Guard, and she had an opportunity to take a position back east. I believe it's in Washington, D.C. And when the big man in your unit comes calling, you go. So she has taken a position which takes her out of her obligation to be able to be with us for the remainder of the year. So the Executive Council has a decision to make in situations like that where it doesn't have to go back to a special election. We can appoint a person. So what we decided as an Executive Council is we would take the next highest vote getter from the election in the fall, offer the position to him or her, which just happened to be Crystal Stout. She's extremely excited. She actually ran against Brian McMillan for the secretary position. But she was excited to join us. She's been interested for the past few years, and she's going to be in there. So welcome to Crystal. I don't believe Crystal's here tonight, but we will see her in October. Okay, quickly, you guys have seen this before. The purpose of our society is to advance professional ideals in the science of meteorology and to promote the development, exchange, and application of meteorological knowledge. That is the Oregon AMS mission statement. Just a couple of quick updates here that we normally go through. Some of these will look a little repetitive, so we'll move quickly. I want to talk about this first one. Oregon AMS membership dues are $10 a year. That is the first increase. It's no longer $7. It's the first increase we've had in a decade. And the reason for that, and I feel obligated to justify that in front of our members here tonight, was obviously we've grown tremendously in the last few years. Anyone who's been a member for a long time has known that. With the additional $3, just that difference in money that we've brought in, we are going to be able to bring in bigger and better presenters for you guys and for our chapter members for years to come. Expenses are high. If we cannot get a facility like OMSI for free, then we're paying for facilities to host any meetings that are larger than, say, 45 or 50 people. So the days of having meetings in pizza facilities and stuff like that I'm not going to say they're going to become fewer and fewer, but on the larger meetings, if we start bringing in larger speakers from around the Northwest and beyond, well then we need to think about a more professional venue that will host them. So I appreciate it on behalf of the chapter. I appreciate your guys' support on that. And like I said, the email I sent out that came actually via John Rainier, our treasurer, National AMS is approaching $100 a year now for a full member membership. That's outside of the student membership, which is nearing 70. So just a little comparison there in the two. Okay, of course you guys all know we're the single largest chapter in the country now, 165 currently paid members, 8 monthly meetings, and those are our meetings that we boast, the big winter weather forecast conference. And we are on Twitter and Facebook. You guys can find us there. We're also on the World Wide Web. Use the search engine, look us up. All right. On to the big stuff. Now, I teased a little bit on Facebook the last day or two. Nancy came just because of the tease, right? Yeah. Okay, see, she admitted it. Nancy Wall is one of our members, and she's joking, by the way. She didn't come just because of that. The Saturday, October 13th, 10 o'clock, right here at OMSI, we're going to be hosting the 50th anniversary commemoration of the Columbus Day storm. Here's what you guys don't know, unless you happen to look on the website, because we leaked it last week on accident. I realized after the fact we'd already posted it. Headline presenter is going to be the National Weather Service office in Portland. We're not sure exactly who yet. Hint, Tyree. Tyree's like, not me, what? They're going to headline the meeting, and it's going to be the nuts and bolts of how the storm formed. They're going to go over all the technical aspects of the storms, maps, everything. You want to know how the Columbus Day storm formed and where it went? From a meteorological perspective, they're going to give a great presentation. I highly recommend everybody show up for that part. Supporting presentations will be given by meteorologist Jim Little, who is here tonight, and KPTV's, back up. Jim is going to give this is not necessarily the order we're going to go in. It's likely the National Weather Service will go first. We haven't got the order for the others yet, but Jim's going to take us back on a little journey backwards in time about how the local media covered some of this event, and including, and several of you may have remembered, it used to be on the National Weather Service's website, the old Jack Capel audio tracks or audio tapes, if that's what you want to call it, Jim. When they were actually sitting there, three of them, talking as the storm was in its fury that night. I remember listening to it probably 10 years ago. There's a gust to 95. There's a gust to 100 right there. And I believe, Jim, they were doing that from the radio transmitter, the old radio transmitter in North Portland.
I'll talk all about that, but among other things, there's an interview with the transmitter engineer who was in the West Hills on the TV tower and was there when it went down.
When it came down, wow. So anyways, great stuff. Jim's got some good stuff to show. KPTV meteorologist and reporter Brian McMillan's working on a sort of a survivor story. He'll probably bring that in the form of a video. So he'll show that video. It'll be a short video. And George Miller, who's sitting right here in the front, retired meteorologist from the National Weather Service, he's going to take us on sort of a historical perspective of the storm. We're trying to get George to also incorporate a lot of pictures into his presentation. George is also a big historian, as you all well know. He's a big weather historian as well. So hopefully we get a really, really good look through his eyes back at the history of the storm from a photographic perspective. And last but not least, windstorm expert Wolf Reed, who, if you guys were here in the October meeting last year at the winter weather meeting, he spoke in the second half of the day, in the second session. He's going to talk about the possibility of a reoccurrence of such an event like that. So he'll look at storms, great storms of the past 100+ years. He'll rank them, and he'll also perhaps take a look at what the odds are of seeing something else. We also have an open call for vendors. If anybody in this room knows somebody who has a weather-related business or science-related business that would like a free table set up just outside those doors on the morning of this meeting, get a hold of myself or any one of the other council members tonight or as soon as possible, and we'll stick you on the list. Right now we have, there's only 5 tables available, and we have 2 that are filled, so we still have 3 tables left. And it's okay if you have something, if you have a product that you're selling. I'll double check with OMSI. We have to pass them all by OMSI, but they haven't had an issue with that in the past. So, all right. Let's see. Oh yeah, there will be a raffle at that meeting as well. We are going to raffle off a Davis weather station like we did last fall at the winter weather meeting. So we'll do that both at the October meeting and again at the November meeting. So Ryan Muehlbach, bring your money. Yeah, exactly. Ryan has, in the last 2 meetings that we've done this, he's probably dumped in about $50 each. So if we get him to do this 2 more times, they'll pretty much have bought the weather station. So anyways, I went right past the November meeting. We'll go quickly through this. That bumps our winter weather forecast conference into November. That is the date, Saturday, November 17th. Right here, headlining will be the National Weather Service, and then Jim Little will be returning again this year. Jim, everybody really appreciated your forecast last year. And Kyle Dittmer will be returning again from the Columbia River Intertribal Fish Commission, and everybody's favorite, George Taylor. All right, so the big question is, who's missing? Pete Parsons. Long story short, Pete and Jim work for the Oregon Department of Forestry, and somebody needs to be on that forecast desk on Saturdays. That's Pete's prescribed day. So it was very tough for him to get out last year. So since Jim's here maybe tonight, we'll say, hey Jim, we cannot not have that one shot of coldest winter since '78 somewhere in your presentation. So it's just we'll just drop some hints there. I know everybody likes that. And
I won't wear a cheese head.
that's right, no cheese head. No Green Bay Packer cheese head. Okay, also we're going to have, of course, Mark Nelson's winter weather recap and Jesse Nicola. He sent in an RFP. He's with Mounted Ski Bowl, and long story short, he's going to do a pretty interesting presentation on how he was able to take extracted data from the National Weather Service's XML feed and design a forecast specifically for Mounted Ski Bowl, and how accurate it is compared to some of the news media broadcasts that are very vague for the whole mountain. So anybody in the ski industry, that'll be an interesting presentation. Okay, 2 seconds on this. Everybody's heard this before. We are still up for Chapter of the Year award. There were 3 chapters that were nominated, and we will not know until the end of October. So we might have some information on that by the the October 12th Columbus Day Storm meeting on the 13th of October. We may not until November. 2 other chapters plus us, so we'll see what happens. Don't need to go through that. That's everything we did last year. 1,400 people attended our meetings. Revenues were up. Increased public outreach. Tackled the tough subjects of the 2 of everybody's favorite meetings last year. But 850 people attended those 2 global warming meetings, and we raised $650 at the door. So yeah, that's pretty good. And that went right back, regardless of which meeting it was at, that money went right back into our coffers. Unfortunately, we did have to pay to reserve some of those rooms, so the money went right back out. But it's just good to know that people were willing to donate at those meetings. All right, and we increased our outreach for people just like Dr. Mantua to come down from up in Seattle. So, can we top it this season? Well, we'll just have to wait and see. Okay, at this point, before we introduce Dr. Mantua, I have a late addition here, and I promised George Miller I would give him some time. George is participating in and planning, with Kyle Dittmer and some other good folks down at Marylhurst University, a climate forum on October 6th. And George, why don't you come on up and tell us a little bit about it, and then we'll get right on with Dr. Mantua.
Thank you, Steve. Well, you should have recovered from the climate change meetings we had 6 months ago. So you ought to be ready for another one then. This is the 3rd climate change forum that Marylhurst University has hosted. And Nate Mantua was at our one, I believe, about 5 years ago and presented. We have an excellent array of speakers. Our keynote speaker is Dr. Anthony Straba. With NASA, he's a microphysicist for the NASA AMS Research Center. He is also a member of the Catholic Coalition for Climate Change, and he's done extensive work in climate change. And he's going to talk on our keynote address science, spirituality, and the work ahead, because we're trying to cover a broad area here, both science and social issues with regard to this particular forum. So there's not a whole lot of it available yet on the Marylhurst website, but I'm sure there will be. I was talking with Greg Darda, Science and Math Director, today, and there will be shortly. Steve has a program agenda, which I'm sure will show up on the AMS website. The AMS website, the local chapter, is also a co-sponsor of this, and we're very grateful for that. So October the 6th, 10 a.m. until about 4 p.m. in the afternoon. Please set that time aside. I have, because I'm going to miss an Oregon State-Washington State football game that day. And yeah, I see a hand go up on the back there to a cheer. So I hope that you'll be able to attend that. I believe there's going to be a box lunch available, and it might be on an RSVP type issue. So pay particular attention to the Marylhurst website. I have one other thing to say, and it's not with regard to that, but on October the 12th, the Oregon Historical Society is opening an exhibit, a 50-year anniversary exhibit of the Columbus Day Storm. And I had a preview of that yesterday. And it's really a nice exhibit that they're putting together for that, and it will probably run for about 2 months. So I'm sure that you may want to take that in sometime over the next 2 months. But please put October the 6th date aside, 10 a.m. to 4 p.m. at Maryland University, and we'd love to have you there. Thanks, Steve.
All right, thanks, George. Thanks, George. I need a drink here. I'm fighting a cold. All right, let's get into the good stuff. See if this works, Bobby. Just like that. Okay, ladies and gentlemen, right over here on my left, Dr. Nate Mantua is an associate professor of aquatic and fishery sciences at the University of Washington. His expertise revolves around climate dynamics and climate impacts on aquatic ecosystems. His research is focused on understanding the dynamics and consequences for natural variations in Pacific climate related to El Nino and the Pacific Decadal Oscillation, and climate impacts on Pacific salmon and marine ecosystems. He served on the Pacific Salmon Commission panel on Fraser River sockeye declines, the U.S. Fish and Wildlife Service expert panel on marbled murrelets, correct? It's fascinating. We got to ask him exactly what those are. And the Royal Society of Canada's panel on climate change and ocean biodiversity, and the Natural Research Council study of the Alaska groundfish fishery and stellar sea lions. He received a Presidential Early Career Award for scientists and engineers from NOAA in the year 2000. And for the past 3 years, he has served as the co-director for the University of Washington's Climate Impacts Group, which is an interdisciplinary research team dedicated to increasing the climate resilience for people and nature. Earlier this year, he was appointed to the leadership team for the Department of Interior's Northwest Climate Science Center. Ladies and gentlemen, from the great city of Seattle, Washington, Dr. Nate Mantua.
I see a couple of familiar faces, but this chapter of AMS does have a reputation for turning out big crowds and really enthusiastic crowds. So Steve's been talking to me for a while about getting me here, and I have been excited to get it into my schedule. Sorry it's taken so long, Steve, but this is a great time to be here because the PDO has been kind of showing its head again after maybe a little bit of time out of the spotlight. Can we turn the lights down a little bit in the front?
Sure.
They're up there.
Bobby knows how to do it.
He knows how to
It's
do it.
actually up there on the podium.
Oh, it is.
And the one's on the top corner, touch screen. Bobby's our resident technology expert. There you go.
Is that enough?
I'm going to do one more. Yeah, we couldn't get a color mic stand for you.
Okay. So, please don't fall asleep on me. I can hardly see you now, so you might do it. First slide shows a picture that ran in Science magazine back in 1992. And this came from work that was never published in a peer-reviewed journal article, but it was a workshop report from a meeting that has gone on in California for a long time called PACCLIMB. And that PACCLIMB is a really interesting annual meeting that's been held in Pacific Grove most years, where people who study water, tree rings, corals, all kinds of different aspects of climate and climate impacts on ecosystems have gotten together and talked about different things that they've been observing and trying to understand. And a very bright guy named Curtis Ebesmeyer, who is now very famous for rubber duckies, because he is the flotsam and jetsam guy who has published a couple of really cool books recently. He's an oceanographer from Seattle who, at the time, had assembled a bunch of different time series tracking things like the large-scale climate associated with the Aleutian Low pressure cell, the abundance of Canadian Greek geese, salmon in the Northwest, Dungeness crab off the Pacific coast, Washington oyster growth, and he put all these things together in a very subjective way because he noticed that most of these time series had some kind of a step change in them between 1976 and 1977. So he came up with this composite index and said, this represents some kind of sudden shift in the climate of the North Pacific. And it was an idea that really did not make a whole lot of progress through research circles in atmospheric sciences or climate research circles for a number of years. And this did not ever result in a publication. But when I was a postdoc working at the University of Washington, starting in 1995 and then in 1996, there was a group of us, including Curtis, who were getting together on a routine basis to look at our time series of different things. And I had started a project focused on Northwest climate, and sure enough, this kind of step change was very obvious. And working with lots of fishery scientists, and we started to put this story more together and ended up publishing a series of papers about it. What I want to talk to you about tonight are first PDO signatures in the climate of the Pacific and North America, the impacts that this phenomena has on forests and marine ecosystems, paleoclimate evidence for its behavior, going back before we started measuring things and writing it down, mechanisms of predictability, and then the last topic, the PDO and global warming. So a bunch of different topics. I'm going to try and cover it in no more than an hour. So I'll ask that you hold your questions to the end. Otherwise, we might be here for a long time. We still might be here for a long time. But the first journal article where this phenomenon was named actually appeared in the Bulletin of the AMS in 1997, and it was actually maybe the first article that ever appeared in the Bulletin of the AMS that talked about salmon. And it did that because fishery scientists at the university were looking at the history of Alaska salmon production and seeing that the whole state's salmon production really boomed, starting in the late 70s and the early 80s, and there was no real clear understanding of why that happened, what coordinated all these salmon runs to start flourishing in a place where the freshwater habitat was pristine. The management was very conservative in the 60s and 70s at least, and they started to build a lot of hatcheries in the 1970s at a time of historically very poor salmon production. But in the late 70s and early 80s, salmon runs were booming everywhere, whether you had a hatchery or not. Well, they turned to climate, and we started to collaborate on this story and came up with a lot of evidence that this pattern has some connection to El Nino. It looks a lot like it, but it plays out at much longer time frames than El Nino does. And we came up with this sort of cartoon of ocean temperatures that is the characteristic pattern that when it's colder than average in the central and eastern part and the western part of the North Pacific, that whole blue shaded area, it tends to be warmer than average everywhere it's shaded red. So that's in the Gulf of Alaska, along the Pacific coast, most of the tropical Pacific, and most of the Indian Ocean. And we came up with a time series for this pattern by just comparing every month's observed sea surface temperature with that reference pattern. And it's shown here, this time history of it, going back to 1900. And if there's a +1 value of that index, the observed temperature pattern looks just like the reference pattern. Warm along the coast in the Northeast Pacific, cold in the interior. If it has a minus value, a negative value, where we shade it with the blue bars, it's just the opposite. Colder than average in the Gulf of Alaska and along the Pacific coast, and warmer than average in that offshore waters towards Asia. So if you look at that history, you see that from the mid-20s to about 1947, lots of those red bars, lots of positive scores. It looked like the map above. The same was true from 1977 until 1998. We had a couple of years here, 2004, 5, and 6 that were mostly looking like that. And then the other years, it was just the opposite. And you'll see that I put in some arrows for periods where we had what our work and other work has suggested you might consider to be phase shifts in the PDO pattern. From cold to warm in 1925, from warm to cold in 1947, cold to warm again in 1977, and then some question marks in the last 15 years. In 1998, a big shift from very warm to very cold conditions, but that cold phase in the late 90s only persisted until 2002. Then a couple of years on the warm side, and then in 2007 a shift back. And since 2007, we've had mostly months and years back in that cold state. And there's PDO fingerprints and records of temperature, precipitation, snowpack, stream flow, marine ecosystems from a lot of places around the Pacific, North Pacific Rim and in the tropics. And this is a comparison of that signature pattern for the PDO on that left panel and the warm state of ENSO, or the El Nino, in the right panel. And the color shading is the sea surface temperature fluctuations, or the deviations from average, that go with this. And there are arrows representing the surface wind stress, which really drives the ocean. And the contour lines are for the atmospheric sea level pressure. So, at first blush, you might say, well, they look pretty similar. You've got a blue spot in the North Pacific, red along the Pacific coast, red in the tropics. But some of the subtle differences are that the blues are even bluer for the PDO in the North Pacific, and a stronger signature, and the reds are even redder up in the Gulf of Alaska. So a stronger signature in high latitudes for the PDO. And the opposite is true for El Nino, a much stronger signature in the tropical Pacific, especially in this narrow band along the equator. So this is really the fingerprint of the El Nino in the tropics. Is the warming of the eastern and central part of the equatorial Pacific, and a collapse in the trade winds. That's what's indicated by these arrows that are pointing this way, meaning of those easterly trade winds. In both cases, though, they do favor an intense Aleutian Low in the North Pacific, and that's where that sort of bullseye of contours comes, and the strengthening of the westerlies over those blue patches of cold water, and an increase in winds from the south to the north along the Pacific coast into the Gulf of Alaska. The other really striking difference in the behavior of these patterns comes with time. That if you look at the PDO time series, it just has a lot more sort of decade to decade variability in it than you see with this index of El Nino, which is an average temperature anomaly in a box centered on the equator. It's called the Nino 3-4 index. So a little bit of spatial difference, big difference in the time variability, but it turns out that this short-term El Nino variability is strongly correlated with the shorter-term variability of the PDO in the North Pacific. And it's because the Aleutian Low is a key driver for those North Pacific ocean temperature variations, and El Nino has a big influence on the state of the Aleutian Low in the winter half of the year. So this is a depiction of the typical sea level pressure anomaly patterns that go with the warm phases of the PDO. And you see that area with the blue contours showing lower than average sea level pressure with the big L right over the Aleutian. So an intensification of the wintertime Aleutian Low. And that wintertime Aleutian Low is the breeding ground for North Pacific storms. That's why you see it here when we average from October to March. It's just averaging over lots and lots of storms that are forming out in the northwest part of the Pacific, intensifying south of the Aleutians, and then starting to weaken as they come to the Pacific coast. You average over lots of storms, and you see that the big low out in the North Pacific, centered over the Aleutians, and that tends to come with a ridge, both in the tropics. You see that H in the lower left-hand corner, and then over the Rockies, and really over western Montana, southwestern British Columbia, where that H is. And the time history for the Aleutian Low pressure cell is shown in this low, and this is an index that is just a box average of sea level pressure in the North Pacific, centered around that pattern that you see above. And where you have the blue bars, the Aleutian Low is weak. That means that the pressure is a little bit higher than average. And where you have the red bars, it's strong. And between this big shift from the late 1970s, the 10 years before and after 1977, the Aleutian Low pressure cell was about 8 millibars deeper in the 80s than it was in the 70s, on average. A really large shift in the climate of the North Pacific. And you can see that that shift isn't unique in the record, that there are a number of sort of decadal shifts that have occurred, and the most recent one is here in about 2007, where we see a lot of these blue bars, weak Aleutian Low years. But in the 1980s and most of the 90s, the Aleutian Low was especially intense. And that was similar to what was more frequently observed back in the 20s and the 30s 1946. So the Aleutian Low has had this interdecadal fluctuation in it. It also has lots of year-to-year variations, and at shorter time scales, we see that the Aleutian Low is varying a lot. Week to week, month to month, season to season. So it's got variability across many different time scales. But this low frequency part is especially enhanced in the PDO pattern of ocean temperatures. And if you look higher up in the atmosphere, here at 500 millibars, there's really a beautiful wave train that emerges, and this is a pattern with high pressure in the subtropics, low in the Gulf of Alaska, high again over Western Canada. And that pattern has been labeled the Pacific North America pattern. And it follows a great circle route from the tropics over northwestern North America, and then there's another low that's sort of off the page here that sits over Florida, in the southeast part of the U.S. So this is one of the real prominent modes of internal atmospheric variability that we see even in climate models that you have fixed ocean temperatures. That pattern tends to have a lot of variability. It's a natural instability in the climate system. You think about the sort of average jet stream pattern, it wiggles around over the Pacific a lot in this expression of the PNA and the Aleutian Low. And when you have low pressure in the Gulf of Alaska, that intensified Aleutian Low, the typical air temperature signature looks like the panel on the left. And this is for October to March, when the Aleutian Low variability is strongest. So what we've done here is we've looked at what's the strength of the surface temperature anomaly that goes with +1 value, which is 1 standard deviation in the Aleutian Low index or in the PDO index. And what you see is about 2 degrees of warming in Alaska, but that warming covers really much of the northwestern part of North America. And there's an opposite sign in the temperature in the southeastern part of the U.S. It's not quite as strong, it's more like a degree of cooling. And then there's a part of the middle America where it's sort of on the nose line. It doesn't have really any correlation or any signature there at all. For us, it's not quite as strong as what you see in Western Canada and Alaska, but it's still pretty strong. It's above a degree centigrade. And then this panel at the right shows the precipitation signature of the PDO. And these red band areas are places with especially strong reductions in precipitation. And this is in centimeters per month, per 20 unit. But you can see in the wettest places you have the strongest reductions in precipitation. So the west slopes of the terrain, the coast ranges, and the Cascades, and even into the Rockies. And in the southern part of the U.S. and northern Mexico, they have just the opposite signature. That when that warm phase of the PDO is in place, the jet stream is spending more time in the southern part of North America, or also bringing up storms and precipitation in the coastal areas of south central and southeast Alaska. And if you think of sort of split flow around this intense Aleutian Low, and the ridging here, leaving us a bit high and dry, relatively warm and dry, while Alaska is very warm and wet, and the southwest is on the wet side. Remember the whole Gulf Coast of northern Mexico. So in our 97 paper, we looked sort of around the Pacific Rim for patterns that are for time series that had some of this variability as a prominent expression. And we just plotted these as anomalies. So Gulf of Alaska winter air temperatures, you can see pretty close correspondence with what we identified as shifts in the PDO state in 25, 47, and 77 from being warm in that period in the 20s, 30s, mostly cold up until 1977, and the early 70s were especially cold. And then a lot of warm years out until this paper was published in the mid-1990s. Coastal sea surface temperatures in British Columbia, you see similar expression, not quite so clean in the late 50s, early 60s, the water temperatures there are actually a little bit warm. You go down the Pacific coast to Scripps Pier in La Jolla, California, and that has a really clean PDO signature in it. And they have a long record of sea surface temperature that's been kept there. And then we looked at stream flow records, and this is the Kenai River stream gauge, which is down on the Kenai Peninsula, just south of Anchorage in the Gulf of Alaska. You can see that signature of low flows in the cold phase, high flows in the warm phase, and then for British Columbia and Washington, we combined the record for the Skeena River, the Fraser River, and the Columbia River into this one composite stream flow record, and you see that kind of opposite condition with low flows during the warm phases, higher flows during the cold phases. So really picking up on that sort of pattern of precipitation, which is also expressed in snowpack. So we say that if you look at North American climate and the PDO, you can look at some of these eras, like the warm phases from 25 to 46, and again from 1977 to 98, that are winter and springtime temperatures, warm in the northwest, cool in the southeast, and precipitation wet in the southern U.S. and northern Mexico, dry in the Pacific Northwest and the Great Lakes regions. And the cool phases were just the opposite. And you'll see that when I list the cool phases, I'm a little bit cautious about the last decade. I'm going to just pick out the last 3 years because they're the strongest expression of the cool phase PDO years, but you could also look at 1999 to 2002. And it mostly looked like that except for, you might remember 2001 and the big drought that we had here in the Northwest, even though we had cool phase PDO conditions. And we've looked globally to see what signatures you might find across other parts of the world outside of North America. And precipitation correlations are shown in that left panel. I'll just draw your attention to 2 places where there's a strong negative correlation with, again, the warm phase of the PDO. The data aren't great for eastern Russia, but you see a lot of blue color here in eastern Russia and the Kamchatka Peninsula. And the data are good here in Australia. You see a lot of blue color there and a negative correlation. So a very El Nino-like for Australia. Australia known to have drought conditions during El Nino years. They also have extended drought periods with the warm phase of the PDO. You might recall that it was a year ago, Australia had phenomenal flooding in Queensland, North Queensland. Coincident with a very strong La Nina year, but they've had big shifts in their precipitation with El Nino and the PDO through time. And if you look at the temperature correlation now, you see that there are strong correlations in the northern part of South America, in the northeast part of Africa, some strong correlations in Australia, and also strong correlations in equatorial and in South Africa. But the biggest impacts really are over North America. That's where you see the big correlations and a lot of the color. So the group that I've worked with at UW has been focused on natural resource impacts and management. I'll show you just a few slides from some of the work people have done that have drawn out interesting relationships with the PDO, and a couple of forest ecologists that we've worked with over the past decade. Turns out there were 2 Dave Petersons working together. So in this paper from Peterson and Peterson, they went up and cored mountain hemlock trees in the Cascades and Olympics, both at the upper tree line and at the lower tree line. And what they found at the high elevation end for mountain hemlock is that their growth was really limited by snow. If there is a really big snow year, they have a very short growing season at high elevations, and those trees don't grow very well. But if it's a poor snow year, mountain hemlock and upper tree line do quite well. And we've got 2 time series plotted there, growth index with the solid black curve, and then the wider gray line is a snowpack history for the Cascades. And you can see the trees grow best when there's low snowpack, and they grow worse when there's high snowpack. At lower elevation, what they found is that those trees actually become water limited in years with a poor snowpack and warm temperatures. And what's shown here is the PDO index and the growth record for low elevation or lower tree line mountain hemlock in Oregon and Washington. And see, the best years for growth there were in the 50s and the 60s and early 70s. Right there, those are the cool wet periods. And then they have some really poor growth years in the 70s and the 30s and 40s. So that's sort of an interesting outcome, that it's not just the species you have to look at, but you have to think about the setting that they're in. And they've used this to do reconstructions of the PDO by finding old trees, go back in time, find the ones that are sensitive, figure out which way the sensitivity works, and reconstruct aspects of the climate. Another aspect that is important for the region is a connection between climate and fire. And if you just sift through the historical records for most of the 20th century, in this case from 1916 to 1997, you see that the area burned during the years with the warm phase PDO just tends to be a lot larger for Idaho, Oregon, and Washington compared to the cool wet eras. The climate has played a major role in wildfire in the Northwest for a long time. And I don't have any pictures in my talk here, but I've collaborated with some forest ecologists who have used fire scar records from much older trees, going back several centuries, to look at the fire scar frequencies through time. And you see that that really still stands up, that across the whole of the West, the warm and dry years, for at least the Northwest, tend to favor a lot more fire, and the cool wet years a lot less. So it's not just about tree management and fire prevention policies, but climate continues to play a big role in the behavior of fire. And marine ecosystems is an area where I've spent a lot of my work. In fact, my academic appointment is in the Aquatic and Fishery Sciences Department. And people have been looking at a number of different fishery-related records for a long time and noticing some really interesting things. Here are sardine landing records for the 20th century for 3 different systems: California, Japan, and the Peru-Chile coast and the Humboldt Current. And you may have heard about the crash, the spectacular crash in the California sardine fishery that took place in the 1940s and 1950s. And John Steinbeck wrote some books about that. Cannery Row, set there where this really incredible sardine fishery was centered in the 30s and the 40s. So that was a huge fishery at the time, and it was paralleled by a very large fishery in Japan during the same era. And both systems really crashed in the 1950s and 60s, and they didn't start to recover until the 70s. The Japanese fishery boomed again in the 1980s and 90s, and Peru and Chile had very productive sardine fisheries at the same time. You see very little indication of recovery for California's fishery, and it wasn't really until the 1990s that California sardines started to become abundant enough again to support a fishery. And in the last decade, we've actually had sardine fisheries in Oregon, Washington, and British Columbia again, like there were back in the 30s. Not as intense, but still productive. So there's been some recovery of the California sardine fishery after decades of just very few fish out there. And this has coincided with the warm phases of the PDO, these booms in the sardine in the Pacific. Farther north, up in the Gulf of Alaska, the fisheries for crab and shrimp were especially productive in the 1960s and 1970s. And these photographs come from trawl surveys that were conducted by Alaska's Department of Fish and Game in a small bay near Kodiak Island. And they used small mesh, trawling near the bottom, and found that in the 60s and 70s, their catches were heavily dominated by shrimp and small forage fish, things like capelin and herring. But in the 1970s, they started to catch more big fish, Pacific cod and pollock, these large-bodied animals. And in the 1980s, those areas were full of fish again, but now it was things like halibut, cod, and pollock. And the shrimp and the small forage fish were completely scarce. And this wasn't happening just in this one place, Pavlov Bay, but also throughout the Gulf of Alaska. And this chart in the lower right shows a history of the catch composition from the 1950s until the late 1990s in the Gulf of Alaska trawl surveys, with the red bars representing shrimp. And you can see shrimp really dominated the catch until about the mid-70s. Cod and pollock with the yellow bars, flatfish with the green bars, and then other things with the blue. But the whole system really went a reversal. It just kind of went into a reverse state from shrimp, crab, to something that was much more large fish, cod, pollock, and flatfish. And that's continued to persist to today. It's been still dominated by some of these large fish. And for Pacific salmon, we have good catch records that have been used to estimate the total biomass of Pacific salmon going back to the early part of the 20th century. And here each color represents a different species. So the green are Alaska sockeye, or Asian sockeye. North American sockeye are here. North American chum are in the blue area. Pink salmon produced in hatcheries are in this hatch box. And what you see are two periods of especially high salmon production over the 20th century. The first one from the mid-20s until about the early 1940s, a period with especially low salmon production in the 60s and early 70s, and then really boom times ever since, up until 2005 at least. And of course, one of the big changes that we've seen in salmon production in the last 50 years is the development of hatcheries to put lots of juveniles into the ocean. And that's not just true here in the Northwest, where habitat has been highly degraded and lost, but also in Alaska and in eastern Russia, and then in Japan as well, where today they produce a whole lot of especially pink salmon. Something like 100 million per year in terms of adults. But even without the hatchery production, you still have this big boom in salmon production. And it's almost entirely at the northern end of their range, in Alaska and in Russia, where most of these fish are returning. The big numbers in terms of biomass of salmon in the North Pacific is pink, chum, and sockeye, and those really productive populations are at higher latitudes. So what's interesting for us is that for much of the 20th century, when things were especially good in Alaska, they were especially bad here, and vice versa. And I just have two time series showing this pattern, what we've labeled an inverse production pattern in Pacific salmon. The red curve representing Alaska pink and sockeye catch, and the blue curve are an estimate for the total returns of spring Chinook to the Columbia River. So a combination of what's caught in the lower river plus what passed over Bonneville Dam. And that record started in 1938 when they finished the construction of Bonneville and started counting fish, going through the fish ladder. And you can see that in spite of all of the things that have happened to Columbia Basin salmon production in terms of habitat modifications, degradation and loss, hatchery production, changes in fisheries management, it still varies a lot through time. And in the 50s and in the 60s and the early 70s, those were pretty good times for Columbia River spring Chinook returns. You come into the early 1990s, those were really bad times. And this is an era of bad times for Pacific salmon in our part of the world, for many watersheds, and different stocks and species. This is the era of ESA listings in the Northwest. And then, in just the last decade, we've seen some changes. We've had some spectacularly good years with Columbia River spring Chinook. The last few years have been pretty good. Not nearly as good as what happened in 2001, where there were over 400,000, but still some recovery. So what's interesting, especially, is that in this period, and in the last decade, there have been a number of years where salmon production has been pretty high in both Alaska and in the Northwest. And it doesn't fit the PDO pattern of prior decades. But it does fit the story about cold conditions off of our coast being especially favorable for Pacific salmon. And this cartoon sort of draws out basically what's going on along the coasts of Washington, Oregon, and California, that when it's cold along our coast, the ocean tends to be weakly stratified, so it's not very strongly layered, meaning that the upper ocean temperatures and salinities aren't that different than the deeper ocean temperatures and salinities. So when the wind blows out of the north, like it does in almost all summers, and that surface water gets swept offshore, upwelled currents bring a lot of nutrients, and they also bring subarctic communities of zooplankton. And those subarctic communities of zooplankton are very fatty little critters, and they include things like krill that are great forage for the things that eat them, including juvenile salmon. They eat krill directly, maturing salmon eat krill directly, but also the forage fish like smelt and herring that are feeding on that zooplankton that are then feeding the predators that eat them, like maturing salmon and seabirds and marine mammals. And when we've had especially warm waters along the Pacific coast, the ocean becomes more layered. You have a relatively low density warm layer floating on top of that higher density nutrient-rich water that's deeper, and it's harder to upwell nutrients. And the community of even the zooplankton that thrive in those warmer waters tend to be much leaner, smaller critters that are not very good food. They're not packing on the omega-3s that we're all told we should have as part of our diet. And it turns out that those fatty acids are really important components of marine food webs. And when it's cold, it's as if we have a subarctic ocean along our coast. It's like having Alaska's ocean at our latitude. And that's where salmon thrive. And when it's warm, it's more like having Baja California's ocean off our coast. And that's not where salmon thrive. So the next topic, paleoclimate reconstructions. If we look back, before we actually have instrumental records for our climate, do we see evidence for this PDO pattern? And a student that worked for me about a decade ago, Sept worked on paleoclimate reconstructions based on tree rings taken from around the Pacific Rim, from Alaska, British Columbia, Oregon, and Washington, finding those trees that had a sensitivity to things like the snowpack in the spring, combined them to create a reconstruction for the PDO going back to 1600, and that time series is shown in this top panel. And if you look at that, well, there's nothing that really stands out just with your eyeball assessment, I think, except that it has lots of variability. What I wanted to share with you here is this panel, which is called a wavelet power spectrum. So what is this fancy thing, wavelet power spectrum, with a pretty picture? Well, if you look from left to right, it's got time from 1600 up until the 1900s. And from top to bottom, it shows period, with very long periods, 256 at the bottom and 2 at the top. And what it does is it measures the energy at different frequencies in that time series as you move through time. So it's taking this sort of local look at what frequencies are prominent in this pattern as we go through time. And the brightest colors are the places where you have the most energy. And what it shows is that back in the 1600s, most of the energy in that time series was in periods from about 16 to 60 years. And then when you get into the 1700s, most of the energy was at periods of about 60 to 80 years, and also around 15 to 25 years. And then in the mid-1800s, there wasn't a whole lot of energy at those low frequencies, a little bit, say around 20 years. And then most of the 20th century, when we do have direct measurements, most of the energy is at about 15 to 25 years and about 50 to 70 years. So what's interesting about this to me is it shows that the PDO pattern, it doesn't have a fixed periodicity. It's not like a pendulum that swings at a very steady, predictable, continuous rhythm. But instead, it's sort of wandering around at different frequencies through time. important aspect for our expectations about how it might continue to play out in the future. It turns out that a number of different groups have done this kind of reconstruction and have found similar results, indicating that there doesn't seem to be a real time scale tied in with the PDO, that it wanders around at different periodicities. Another reconstruction that was done by a student I worked with relied on some other material. It relied on gooey ducks, this creature that this guy is holding up in the air. So the gooey duck is a delicious clam, a bizarre looking creature, hard to dig because they're powerful diggers. They can live up to at least 160 years of age. And it turns out that in some locations, their growth is correlated with the environment that they're in. And temperature, it turns out water temperature during the growing season is correlated with gooey duck growth in some locations in the Strait of Juan de Fuca. So Ari Strong, who now works for Washington's Department of Fish and Wildlife, in their shellfish program, as a master's student, he got a collection of gooey duck shells that came from a location just in the east side of the Strait of Juan de Fuca. Here's Puget Sound on this map. That X is Protection Island. So if you know the area, it's close to Sequim, out of the straits. And he took very thin sections from the hinge area of the clam, and that's what's shown in the photographs at the top left. And then he shined light through those sections and digitized the growth bands. So they grow a lot in the summer when food production is really high and the water's warm, and then they don't really grow at all in the winter, and that's where the dark bands are. You can go back and count these rings, just like you look at tree rings, and look at the increments, good years and bad years, and you can see that there's some really good years, this wide bands in 1998, 97, 96, 95, really wide band. Going back in this photograph to the 60s, the cold years, just notice how much narrower most of those bands are. This clam did not grow so well in the 60s, and he found that if you get lots of clams and you compare their growth histories together, they have a lot of shared variability, just like trees. Really cool project. And again, he had some clams that went back to the 1860s. And the red curve is the reconstruction, and the blue curve are actual measurements of ocean temperature in the Strait of Juan de Fuca for the growing season, March to October. And just an interesting pattern. It showed that there was something unusual about the 1980s and 90s. You know, a lot of warm years here, but there were warm years and good growing years in the 20s and 30s. And then not so much when you went back into the 1800s. And the worst growth years were that really cold period in the 1970s and also a really cold period in the early 1950s. So the clams tell us that, yeah, PDO looks pretty important to them. And I should say that he did experiments in the lab and found that temperature really was the controlling factor, that he would put a full ration of food in the tanks and grow these clams at different temperatures, and found that the ones in the warmer temperatures, they did best. The colder temperatures did worse. So what about using information about the PDO and climate predictions? One thing that is pretty clear is that the hydrology of the Northwest is very sensitive to the PDO because it hits it in a way that the temperature and the precipitation work together. It favors either cold and wet or warm and dry. And that combination is compounded in the snowpack. It's both cold and wet. Precipitation collects in big snowpacks, and by the end of the snow season, we have a big snowpack. And if it's warm and dry, it just goes the other way. So Alan Hamlet and Dennis Lettenmeyer, who are civil engineers at the University of Washington, have done a lot of work looking at the Columbia River and its flow history. And here they're just looking at the snowpack contribution to flow. And what they did is just split the record according to the phases of the PDO, and also then pulled out the El Nino years and identified those Ninos with the red diamonds and the La Nina years with the blue triangles. And you see that both El Nino and the PDO have tended to flavor the amount of runoff that's come through the Columbia River. That the high flow years, mostly in the cold phase of the PDO, the low flow years mostly in the warm phase, and the combination of a warm phase PDO and El Nino gives you most of the really low flow years, these red diamonds. And a combination of La Nina with the cold phase of the PDO giving you most of the really high flow years, and these are the blue triangles. And the fluctuation around the mean is about plus or minus 10%, so the difference between cold phase and warm phase periods is about 20%. And flow in the Columbia River is actually a pretty important thing to keep track of because it is fuel for hydropower, it is water for irrigators, it is habitat for fish. And it has a big part in the economy of the Pacific Northwest. So they've done a lot of work looking at the predictability of stream flow and how that might support water management. And it also brings out sort of an interesting thing that we see is that the combination of the state of El Nino and the state of the PDO looks to be very important. And that when they're both pointed in the cold direction, you do tend to have a stronger expression in North American climate. And when they're in a mixed pattern, where say it's warm PDO with La Nina or cold phase of PDO with El Nino, it doesn't tend to have nearly as regular or strong impact on North American climate. So this pair of panels is just for La Nina years with the cool phase of PDO, looking at precipitation. This bottom panel, lots of blue color, shows the strongest impacts in the Great Lakes, the Ohio River Valley, and also in the Pacific Northwest, in the northern tier of states. But when we have the warm phase of the PDO and La Nina, there's not much to really hang your hat on for North America. A little bit of signature in Idaho's precipitation, but not nearly as strong. And the same thing works in the other combinations. Cool PDO, El Nino, it really doesn't tend to flavor our climate very strongly. So keep that in mind when you think about the upcoming winter when it comes to the sort of the outlook for PDO and El Nino. So I said that El Nino and PDO are closely related. And there have been a lot of work in the last decade that has sort of looked at this relationship. And one of my former classmates from graduate school, Matt Newman, who's now working in Boulder for NOAA, published this really interesting paper where he hypothesized that the PDO, its dynamics, can really be boiled down to two things. The first one is a tendency for persistence. What happens this year tends to be followed by the same thing next year. And the second thing is the state of El Nino, that El Nino tends to kick it in the direction that El Nino is flavored in for that winter. So if you have an El Nino in the tropics, it favors a deep, intense Aleutian low. That tends to reinforce the warm phase of the PDO. And when you have La Nina in the tropics, it favors a very weak Aleutian low and then tends to push things towards the cold phase of the PDO. And he put in a very simple equation that you can use to make a prediction 1 year in advance. The PDO value for next year is 0.6 times the PDO value for this year plus 0.6 times the value of that ocean temperature index in the tropics for next year. So you have to forecast this one first. And it turns out that there's a lot of effort aimed at forecasting the state of El Nino. Every month, about 25 different groups put their forecasts together, and you can look at those. I didn't actually include the forecast for El Nino in my slides, but most of them are sort of pointing towards a weak warm event in the tropics. And this is what the ocean temperature anomaly pattern looks like for the last month. So from August 12th until September 8th. Where you see the yellows and reds, that's warmer than average. Where you see the blues, it's colder than average. So there's a big band of warm water in the western and central part of the North Pacific, very much the warm or the cold phase of PDO signature, and also the cold water in the Northeast Pacific in this horseshoe region. So that's the cold phase of the PDO in the North Pacific. And in the tropics, if you've been watching that lately, we came out of a pretty strong La Nina this winter, followed an even stronger La Nina last winter. And the last few months it's been warming up. So there's this bit of warm water in this band along the equator. It's disconnected from the coast. So if you're a real aficionado of El Nino, you might have heard of Central Pacific warm events. A new flavor of El Nino. It's getting a lot of attention in research circles. It's this characteristic of warm events that has been repeatedly observed in the 1990s and 2000s where it's not connected to the coast of South America. It's mostly offshore. And this one is so far mostly offshore. It's quite weak. The tropical atmosphere doesn't seem to care about it, which is interesting. Because for an El Nino to really take off, the trade winds have to collapse, or at least get weaker. The trade winds have not really cared about this so far. So I think that it might fade away, or just continue to be very weak throughout the winter, but it's going to be a factor in the upcoming forecast and in the upcoming evolution of ENSO. So right now, I would say we have cold phase PDO plus very weak El Nino in the tropics. The forecast, given that, well, the PDO for this year, and the year that Newman's paper defined, was really more of a Pacific climate year. Start in July and end in June. You do that because most of the action in Pacific climate really plays out through the winter. That's when El Nino peaks. That's when the El Nino influence on the North Pacific is strongest. So center of the year from July to June. So July of 2011 until June of 2012, the PDO index value is minus 1.4. My sort of bracket of the ENSO outlook for the next year, again, July of this year until June of next year, it's going to fall into this category, I think, from 0 to +1. And I'm sort of tending towards 0 myself, but some groups are tending towards +1. And that gives us a range of the PDO values of about -1 to -0.2. So my expectation is, you know, we might have this kind of weak, weird El Nino in the tropics, but the PDO is, I think it's going to hang in there. There are other groups doing PDO forecasts in other ways. The Climate Prediction Center at NOAA runs a full-blown ocean atmosphere climate model, and they're running this model 40 times every 10 days to generate lots of ensemble members to look at the statistics of where does climate go in the next 6 months from the perspective of this climate model. Most of this climate model skill comes in its ability to predict the evolution of El Nino. Each box here is a different month set of forecasts. So initial conditions from, well, this one is April, this one is June, this is August, October, December, February of 2012, here's April of 2012, June of 2012, August of 2012. The black curve is the actual PDO index. The blue curve is the 40-member ensemble average of one of these forecast experiments, and the red curve is another 40-member ensemble average of another set of experiments. And then all the little light curves, the sort of spaghetti, is the individual model runs. So a couple things I wanted to point out is that from last April, the climate models thought that the PDO would fade back towards average, but it did not. It stayed on the negative side. They both went towards 0. From October, you know, this whole spaghetti diagram mostly captured where the actual PDO went, so you might consider that to have been good forecast. You want your forecast to actually include where the climate went. February of this year, forecast again, trending towards zero, probably not a great forecast. And I've looked at these for the last couple of years. My impression is that it doesn't do a very good job. It just doesn't do a very good job. And this year, it is developing an El Nino in the tropics in the climate model, and it is fading the PDO away. And I just blew up the latest forecast in this panel. That's the forecast from August. You can look at these on their webpage. Sorry, I didn't choose a bigger contrast for you there. But they're consistently going for El Nino and a weakening of the PDO. My guess is that's not going to happen. Not as strong as what they've got, at least. So last topic is the PDO and global warming. I didn't mention one thing that we did in our original analysis to try and get the global warming signature out of North Pacific climate so it doesn't contaminate our PDO analysis. So what we did is we took the observed ocean temperature anomalies for every month for the North Pacific at every grid point. And then we created an index for the global average ocean temperature anomaly. So now one number for the whole planet. Subtracted that off of every grid point in the North Pacific. And we did that through time. And if you're familiar with global average temperature history in the 20th century, it's mostly doing this, going up. So it has introduced a cooling into our data set that doesn't really exist. But it's uniform cooling. It's the whole Pacific is cooling everywhere. And making the whole Pacific cool off, comparing it to our reference pattern, which is shown here, which you get a warm state of the PDO for cold temperatures there and warm here, means that this part of it favors the warm state of the PDO. Kind of surprising, hard to think about maybe, that when we subtract off global warming, we're pushing our index to a warmer state, to a higher number. That's because there's more area in blue than there is in yellow and red. It's not a perfect cancellation. And I'll show you, this index is produced by NOAA. They don't do this step. This is their version of the PDO index just for the last couple of years, starting in 2008. And you see that they have lots of negative scores, and these scores are a little bit more negative than the ones that we produce at the University of Washington. And here's what the index would look like if you didn't remove the global warming, this top panel. You would just see a lot bigger negative values in the last 15 years. These big negative values started in 1998. This is the index that I update every month. This is what it would look like if we didn't remove global warming. The difference between the two are shown here in this bottom panel. So you see there is a long-term trend going upward, and it looks a lot like the global average warming trend, which is shown here. So that's one little wrinkle in what we've done with the PDO index, is we've tried to get rid of global warming from this pattern. And maybe that's not a good idea, because it's confusing things a bit. And here's another thing that's interesting about global warming and PDO. If you look at the observed temperature field in the period from 1998 to 2012 and compare it to the previous 2 decades, from 1979 to 1997, so subtract off that previous period, this is what ocean temperature changes look like. The darkest colors are 1 degree warming. The darkest blues are about 1 degree of cooling. So the world has been warming in the last 20 years relative, or the last 15 years relative to the previous 20. But the Northeast Pacific is about 1 degree colder. And, well, parts of the Southern Ocean are about 1 degree colder. And there's a cold spot south of Greenland, but actually over the last century has remained not moving very much compared to the long-term average. But that's pretty interesting. The world has been really warm in the last 15 years, but the Northeast Pacific has not. If you look at surface temperatures for the
most states have not. There's actually a lot of blue right along the coast and some blue into western Washington,
Western Oregon, and California, that things have actually been a little bit cooler here in the 2000s than they were in the 90s and the 80s.
And here's time series that sort of look at how this has evolved through time. The sea surface temperature record, just average temperatures in a box here in the Northeast Pacific from 1900 until 2011, compared to the land temperature index that a postdoc that's working me created, just on stations that are right on the coast.
And these go from California, Oregon, Washington, British Columbia, and Alaska, so all the way around the Pacific Rim.
And it turns out that air temperature for the coastal cities or coastal towns and the water temperature in Northeast Pacific, their fluctuations are highly correlated. They almost lay on top of each other. Not perfectly, there's some interesting differences in them that we don't quite understand, but there's a lot of shared variability. The correlation is 0.83 between those time series. And you can see how warm it was in the 80s and the 90s. 1999, big cooling, sort of moderated, a couple of warm years in the mid-2000s, and then starting about 2007, mostly cooler years.
So my point here is that the PDO and its year-to-year, decade-to-decade wanderings has a huge impact on what happens in the Northeast Pacific, what happens along the Pacific coast. And it can lead to cooling at a period of global warming for our region. And if it were to reverse next year, it would probably throw us right back up into those especially warm years, like the 1990s,
where we had just a lot of really warm years.
And that work is going into a paper that Jim Johnston and I are working on right now. And Chris, if you're going to the EPOC meeting, you'll see his talk.
So just to summarize and wrap it up,
You know, over the past few centuries, the PDO has been an important part of climate variability. And it's played out at periods that are comparable to a human's lifetime, so that if you say, it used to be a lot colder, things have changed, and you lived in the Northwest, and you grew up in the 40s and the 50s, or the 50s and 60s, you're right. The 50s and the 60s and the early 70s were a lot colder than the 80s and the 90s, but if you have kids, they might say, well, geez, it used to be a lot warmer back in the 90s, at least for a while. So it can actually flavor your perspective of, you know, what's normal here, because it's changing pretty slowly. Even though it doesn't have a preferred time scale, it's tended to play out over decades. And it's had a big impact on our forests and on our water supplies and on our fish. And it has thrown a wrench into a lot of our planning, because there have been politicians that say, I am going to double salmon runs in my 4 years of office. Well, if La Nina and the PDO say it's okay, maybe you will. But if they say no, you are not going to do it. The ocean won't support it. The rivers won't support it. And there is some information in this pattern that provides some assistance in narrowing down our expectations for what's going to happen with our climate. So it can help with climate forecasts, but its predictability is probably not more than 2 years, unless there's something really fundamental that we're missing. And a lot of work is going into this. There's a whole set of experiments that are going to be summarized with this next round of IPCC reports, if you followed any of that, that will come out next year in 2013. They've been organizing what they call decadal climate experiments, where the people that are running climate models to look at the next century are also running them to make 5-year forecasts and to see how well they perform in a hindcast mode for the last 50 years, that they play this game and say, if we had today's technology back in 1960, what would we have predicted for 1960 to 65? And they did that every year all the way up to present. What they found so far is almost no capacity to predict northeast Pacific climate beyond about a year. El Nino is a lot of help. Beyond that, the next year, and the persistence of the PDO is a lot of help. 2, 3, 4 years in the future, they're not finding anything. And that's different than in the North Atlantic. In the North Atlantic, the same experiments are showing that there's actually some hope, because the North Atlantic has this crazy persistence. And it's gotten a name called the Atlantic Multi-Decadal Oscillation. And at least in the last century, this pattern has played out over about a 60 or 70 year cycle. But it may not actually have a preferred time scale either, because as you look further back in time, it looks like it's just a whole lot of persistence, that when it's warm, it stays warm for 20 or 30 years. And then when it gets cold, it stays cold for 20 or 30 years. And then the last point, that the PDO variations can either mask or amplify what's going on globally. That the whole northern hemisphere, it is warming. There is no way to deny that. It's happening. But if the wind blows out of the north, it's cold. And if the wind blows out of the south, it's still warm. And those wind patterns have a very big impact on ocean temperatures in the Northeast Pacific, and ocean temperatures and the wind together flavor the climate that we experience here. So I'll stop with that, take some questions if you have some. Thank you very much.
I'm curious about whether or not you have any information on the volume and rate of flow of the Japan current and exchanges over the last 2 decades. Because I was thinking that it might affect the temperature of the
So the question is, do I have any information about the volume of the current that runs along Japan, the Kuroshio, which is a warm water current bringing tropical water up to high latitudes, and then it peels off at about the latitude of northern Japan into the mid-Pacific? I don't. An interesting thing about the changes in the wind that come from variability in the Aleutian Low is that they cause the upper ocean to get thin or thick. If the wind pattern that we see with the really deep Aleutian Low persists for a whole winter or for a couple of winters, what it does is it tends to raise the thermocline. It thins the upper ocean. And the ocean has some really interesting dynamics, because when that happens, it doesn't just sit there, but it starts to slowly move to the west. And it takes a few years for that disturbance to get close to the coast of Japan. So it actually lifts the thermocline across the whole Pacific. So when we have a whole set of decades, like the 80s and the 90s, where the Aleutian Low is intense, it raises the thermocline and it causes this slow-moving disturbance to lift the thermocline around the Kuroshio, that current, and accelerate the flow. So it does change the position of the Kuroshio and its strength in response to the wind forcing, and it does it in a way that, let's see if I remember how this works. Yeah, well, I think it does tend to reinforce what we see in the ocean temperature disturbances. It sort of fills in that whole pattern. So, yeah, when you lift the thermocline, it makes it cold. The cold water gets closer to the surface. It cools off the coastal areas of Japan. So it's definitely tied up in what you see in the ocean temperature pattern. But it's something people have had a hard time really pulling out of climate models and their climate records, is a strong influence of ocean temperatures in the North Pacific on the weather and the climate. That it's mostly the atmosphere driving the ocean in the mid-latitudes. In the tropics, it's very clear that changes in ocean temperatures have a big impact on the winds, and that then changes rainfall patterns that can disturb the jet streams and have a big impact on global climate. That's why El Nino is such an important organizer and disturber of global climate. But in the mid-latitudes, it's been harder to tease that out.
What's the last word there on your summary?
Snowy, sorry about that.
Notice on one of your earlier charts, there's a pretty sudden shift over time from a cool phase to
Yeah, so what is the mechanism of the abrupt shifts? And let me show that picture. Yeah, so especially in 1977, went from very cold conditions to very warm conditions, and just across one year. And you look at other years, it's maybe not so dramatic. 98, 99, that was pretty dramatic, but it didn't stick. Other transitions were more subtle. One possibility is it's just sort of chance that a few things lined up, like an El Nino followed by a La Nina. That was definitely the case in 1998 and 1999. June of 1997, the tropics started to warm up, and they started to warm up really fast. Really, it started in May. And at the same time, the Aleutian Low was intense, even in the summer in the North Pacific. Very unusual. And it persisted all the way through the winter of 1998. But when you got into April and May of 98, everything shifted. Big La Nina set in, the Aleutian Low got weak, Northeast Pacific started to cool off, and that's what we see here, is a shift between El Nino and La Nina that was coincident with conditions in the North Pacific. That doesn't always happen. And in the 1970s, from 76 to 77, we did have a sort of modest El Nino in 76, 77. It was not remarkable, but the Aleutian Low changes were very remarkable. And that's what caused that. And it's not clear, why that happened, if there's anything to make of it other than coincidence of things that may or may not have been related. And that sort of situation in the late 40s or in the mid-20s just wasn't nearly as dramatic. But there's no good handle on that. Sort of the leading idea now is coincidence.
So what does your data set look like now in the North Pacific for modeling? Has it improved? Do you have the density in horizontal and vertical to do a better job? And preface that question with the fact that I thought I heard you say that the models aren't doing all that well, so has data helped in any way?
The data collection effort has improved dramatically. I had a figure in here that I took out on the train today because I didn't want to go on forever. For this system called Argo, which is a profiling, set of profiling floats. So we have deployed thousands of profiling floats in the global oceans in the last decade or so. And it's basically global coverage. There's about 1 every 3 degrees of latitude and longitude. And these floats spend 10 days at a depth of, I think, 1,000 meters, measure temperature and salinity, then they float to the surface. They take a profile of temperature, salinity, get to the surface, send that observation satellite, and then they go back down. They do that every 10 days, and they last for, a year, 2 years, if you're lucky. They have to be redeployed if they die. So it's starting to give a global picture of the structure of the upper ocean. And that structure of the upper ocean is critical for understanding where the heat is stored in the global climate. Because that's where most of the heat storage and variability takes place, is the upper ocean. And that information is now being fed into ocean circulation models that are assimilating this in the same way that our weather forecasts are assimilating weather observations, so that we get this global picture that is actually accurate view of large-scale ocean state. In spite of that, the climate models that we have today have some real biases in dealing with tropical climate and dealing with the behavior of El Nino. And because El Nino influences the climate everywhere, that means that we have deficiencies in fundamental parts of climate variability. People are working really hard to improve that, but we're not there yet. People are still working really hard to improve it.
Is it possible, or has anybody been able to determine any PDO phase lengths from other proxies like ice core samples or ice core analysis?
One ice core analysis that I'm aware of that was tied to PDO came from a place in northern British Columbia. I think well, it might be southeast Alaska, it's called Mount Logan, but it's in that area where North America sort of makes the turn in the Gulf of Alaska. And it was not the best place to keep track of the PDO, but that's the only one that I can think of where they've actually used a long ice core. The snowpack in the Northwest has been really good, but we don't have long ice cores from our glaciers here because they just accumulate so much and move it so fast that we don't have places that are accumulating slowly and many, many years in one place. So,
considering that Japan is upstream of us, well, that was certainly the Japanese have done a tremendous job of sampling the networks of ocean and atmospheric variables for about a century. Do you ever do a resolution visual analysis of data sets like those that we found around Japan?
Yes, the question is, the Japanese have done a great job of monitoring and measuring their ocean and atmosphere around Japan for a long time. And do I ever do analysis of the data that they've collected at that region? I haven't, but one of my friends and a colleague named Shishiro Minobe, who works at Hokkaido University, has done a lot of work with that, and he's developed some long temperature records from around Japan, just combining the ship observations, and he's shown that a lot of this kind of multi-decadal fluctuation in Japan's coastal ocean temperatures is part of these PDO variations, the larger scale pattern of climate variability. So he's done some really interesting things with that.
One more question. Is AR5 going to present any surprises that you are aware of? The assessment of report number 5 for the IPCC that would be based on some of your research or the research going on in North Pacific? Because there's been a lot of chatter about the low ice pack up in the Arctic, and just last week they had the lowest reading on record. And so anyway, what do you think is going to happen? Is there going to be any surprises on the warm side or the Arctic? Because I'm kind of, if we're going into a cold PDO, but then the Arctic ice melt's been so significant, I'm trying to tie all that together.
I don't know. I haven't been plugged into that whole process. Some of the papers that have been published on the early analyses of the model performance, and especially around this prediction, I think one of the big surprises is that, well, maybe it's not a big surprise, but the sobering message is that the potential predictability of climate in the North Pacific looks to be pretty low beyond about 2 or 3 years into the future. Whereas the potential predictability of climate in the Atlantic is probably a lot better. And part of that, I think, is because the Atlantic doesn't have an El Nino. That El Nino really disrupts the climate of the Pacific. And if its fundamental dynamics are such that the predictability is limited to just a couple of years, that really puts a squeeze on the ability to predict most of the North Pacific climate beyond a couple of years. Even though we have this pattern that plays out over decades, it may not have something like a flywheel that has enough inertia in it that you could monitor the right thing and put it into a model, and it would evolve along some deterministic pathway that gives you more than a few years of predictability.
I'm told that there's some dead zones in the Pacific that's driving fish in the Pacific coast, explaining why there's a Dungeness crab harvest in August from the east. Have you heard anything like this year?
I think I did hear that there was very low dissolved oxygen along the Oregon coast again this fall. So, starting in the early 2000s, 2001, people started to document broad areas of very low dissolved oxygen up on the continental shelf off of Oregon. In most of the years of the last decade, that has happened to some degree or another, and in some years very dramatic. 2006 had the most dramatic. I don't know, Chris, you can correct me if I'm wrong, but there was anoxic water, meaning no oxygen, dissolved oxygen in the water, all the way up onto the continental shelf into shallow water, and big kills of Dungeness crab and other creatures that can't move around very fast on the bottom. And that happens for a couple of different reasons. One is the water that gets upwelled onto the continental shelf is said to be old. It hasn't been near the surface for a long time, so it hasn't been replenished in oxygen. And the oxygen that's in the ocean comes from either direct communication with the atmosphere or photosynthesis. The phytoplankton, one of their byproducts is oxygen. But when organic material sinks and it decomposes, oxygen is consumed. And if water has been in the ocean for a long time, well below the surface, and that consumption process is played out, you don't have much oxygen in deep water. And that deep water is getting upwelled all the time. So you can have just the upwelling, the physical mechanism of pumping depleted water onto the continental shelf. And then if you have big plankton blooms at the surface that sink down and then rot at depth, it consumes even more oxygen. So this is something people are monitoring very closely, and there's pretty good evidence that what's happened in the last decade on the Oregon coast seems unusual. Off the Washington coast, they've documented that for at least 50 or 60 years. It's just part of what happens in the fall every year, to one extent or another. So it's got people concerned because oxygen is a necessary element in the ocean for supporting marine life. And if it becomes more widespread, happens for a bigger window of time, it's going to have big impacts on the ecosystem, especially things that live near the bottom and aren't very mobile, that can get away from it.
Just wondering if you could give us a 25 word or less description of the PDO suitable for a lay audience. What is the mechanism?
Well, I would say that the 25 words, slow moving El Nino. It's like El Nino's slow cousin. It just plays out at a much longer time frame, and it tends to be more evident away from the tropics than El Nino does.
Let me tell you why I ask. I'm going to go back to the Department of Forestry and give briefings to people who know less about this than me. And I'm looking for a good description, good thing to say.
Yeah, well, I think if you look at our climate history, you see that we have decades that are tending to be cool and wet or warm and dry, and we know that that is actually tied up with this very large-scale change in Pacific climate. And it involves the circulation of the Aleutian Low, the positioning of the jet stream, and you see it in ocean temperatures, and it also shows up in our historical records for things like wildfire in the west, stream flow throughout the west as well, and snowpacks. So it shows up pretty strongly in our hydrology, and it's important for forest ecology. Hopefully that's helpful.
Any southern hemisphere reflection of PDO or counterpart to it?
Well, people in Australia have done similar work, and they came up with this label IPO, Interdecadal Pacific Oscillation. And what they did is they took global ocean temperature observations, and then they did it's called low-pass filtering. They smoothed out all the variations at periods less than 13 years. They analyze the data, they come up with a pattern that looks exactly like this. And it has a big impact on eastern Australia's precipitation and temperature history, and the ocean temperatures in the South Pacific. So definitely, and then there's been some other work looking at the hydrology of rivers in South and Central America. And it does have a lot of symmetry with what I talked about tonight, that this seems to be very symmetric. The ocean temperature response, we don't have nearly as good observations of the ocean in the southern hemisphere as we do in the northern hemisphere, so we don't have long time series. But in places like New Zealand and in South America, Australia, you know, they have good observations there. And they do see this kind of mirror image of a lot of what I talked about today. Yeah.
I just wanted to confirm that it seems as though what you were saying was that the cold phase PDO attributes tend to be reinforced by El Niñas and vice versa, El Niñas and warm phase PDOs. And when they're opposite of each other, they have a tendency to cancel and make fairly benign, less strong Pacific Decadal cold phase or warm phase.
Well, it also just sort of less robust, meaning it's sort of kind of be anywhere, but just not repeatable. It doesn't tend to do the same thing. It just tends to just be either one way or the other or in the middle. So that when you average over all those years, you just don't see an interesting pattern.
And in response to that, over the years here, our various weather meetings, it's kind of been concluded that we've had, when there's a La Nada year, we tend to have our most extreme events, like windstorms and snowfall of any size. And none of this data seems to back into that up. I was just curious if you've done anything more on that.
Well, I mean, one thing is that the extreme events don't necessarily look like the whole winter. So when we have really big flood or Pineapple Express storms, they don't necessarily look like the winter as a whole. And also those don't fit the sort of PDO and ENSO category, that those are warm and wet instead of warm and dry or cold and wet. So they're sort of in a different plane than what the PDO and El Nino tend to do.
Yeah.
Yeah. Yeah.
Does, you found any correlation with sunspot activity or geomagnetic radiation or solar radiation?
Yeah, so I haven't looked at that. Scientist at Scripps, Dan Cahan, a great climate scientist, he's looked a little bit at this with some of his colleagues and collaborators and found that there's something that, you know, there might be there. But what they did, they ran climate models and input the sort of subtle changes in the intensity of the sun over the 20th century, estimated from sunspot cycles, and found that the climate model that they looked at actually amplified that a little bit through the tropical Pacific, through changes in the statistics of El Nino that then sort of played out to some degree in the North Pacific. But it wasn't very strong. It was really subtle. And there's been some additional work by other modeling groups, like at NCAR, to look at this. And, you know, it's not very compelling to me, but people keep looking. But it hasn't gotten to the point where people would do the climate modeling and say, we're going to put this into our forecast and see that it actually gives us skill for the next year or the next decade. It's still a research question.
Any more questions for Dr. Mantua? All right. Did we have one more back there? Did I see your hand going up? Go ahead.
It's not specifically what you're talking about, but getting back to the Arctic ice pack melting, since there's been such a short period of keeping track of that, how can we know what normal is?
Well, yeah, so the question is, how do we know what normal is? Normal is a changing climate, without question. A normal climate is moving around. I think, you know, with the Arctic ice pack and with Greenland ice sheets melting rapidly, coincident with hemispheric warming, it's hard not to see that as being pretty unusual, if not really unusual, in the context of the last century. It's not like we don't know anything about the history of Arctic sea ice, because people have been going to the Arctic for a long time and writing down the things that they've observed. And they've observed a lot of variability, and they've observed warm periods in the past. But at least for a century, no one's observed ice-free summers in the Arctic. And it looks like we're not too far away from that we continue on this trajectory. And just the pace of change has been remarkably fast compared to with what the experts, and I'm not an expert in sea ice or in ice sheets, but what I hear from the experts is, this is shocking. And when I go to the EGU meeting, the big national meeting of all the geophysicists in the world, and for the last couple of years I've gone to see what the experts have to say about Greenland. And my impression is they're pretty shocked. That it could be that they just didn't understand the system that they're working in, but they look at the changes in the last decade and they are saying, holy smokes, things are changing so much faster than we thought was possible that yeah, we don't really understand how this system works.
Kind of a nasty corollary to that is we may have already gone past the tipping point and haven't realized it. If we go turning back, we will face real consequences.
All right, one more round.